Pilot orientation for low visibility landings. This film was produced at the University of California's UCFAA Fog Chamber, Richmond, California, sponsored by the U.S. Federal Aviation Administration. A presentation of visual material for pilot orientation for low visibility landing conditions. For uniformity, various standards were used throughout the filming. Any deviations are specifically noted in the titling. All cockpit scenes were taken in the Pan American World Airways 707 simulator. All simulated low visibility scenes were taken at the UCFAA Fog Chamber. Standard conditions: aircraft Boeing 707, cockpit cutoff angle 14 3/4 degrees, pilot's eye height at design point, attitude pitch up plus 1/2 degree, speed 135 knots, 5 knots above reference speed, glide slope 2 1/2 degrees, aim point 1,000 feet past the threshold, touchdown 1,200 feet past the threshold, coupled approach to 100 feet. Fog chamber, fog visual range as appropriate. Lighting system, a KO Category 2. Daylight and dusk, Step 5. Night, Step 4, approach and edge lights. Step 5, threshold, touchdown zone, and centerline lights. Part 1, visual orientation. Static, clear night view of a KO lighting system. This is the standard approach light system for Category 2 adopted by ICAO. It is the basic U.S. system to which has been added a white crossbar 500 feet from the threshold and red barrettes from the 1,000-foot bar to the threshold. These ICAO additions reduce the chance of misinterpreting aircraft distance from the threshold and speed the pilot's recognition of his position. Clear night view of a KO lighting system, normal centerline approach and landing. This approach is on a 2 1/2 degree glide slope. One of the best tools a pilot has under low visibility conditions is a vivid picture in his mind of what he expects to see. Then, when he gets visual cues, he can rapidly identify them and determine if he is properly positioned to continue safely. Normal centerline approaches and landings, 1,200-foot visual range with 3 levels of background brightness, night, dusk, and daylight. The first approach is night. There are the approach lights. Notice at night there is good contrast between the lighting and the background. The painted runway markings play only a small part in identifying position on the runway. This next approach was done at dusk. Here, the contrast between lighting and background is much lower, and as the runway comes into view, the painted markings are a great help in determining the distance into the runway. This approach was in daylight condition. there is a marked drop in the relative brightness of the lights. As is expected, the runway painted markings play an even greater role in identifying position along the runway. Diagram showing the effect of change in cockpit design cutoff angle on visual ground segment. Cutoff angle is defined as the angle between the longitudinal axis of the fuselage and an inclined plane below which the pilot's view is blocked by some part of the aircraft. These diagrams show three cutoff angles. The top is 10 degrees, the middle 15 degrees, and the bottom 20 degrees. As you can see, the larger the cutoff angle, the greater the ground segment that can be seen. Proper seat position will ensure that you have the maximum available. Also, the pilot's apparent cutoff angle varies with aircraft body angle. Body angle is a function of airspeed in relation to V-thresh. 5 knots of speed reduction will increase body angle 1 degree and thus reduce the cutoff angle and visual ground segment. A static study of the effect of aircraft speed on visual ground segment. Initial speed, 135 knots, or V-thresh plus 5, increasing to 155 knots, V-thresh plus 25, and decreasing to 125 knots, or V-thresh minus 5, and returning to 135 knots, 1,200 feet visual range, night. Since body angle does not vary with gross weight, this would be the normal apparent cutoff angle at V-thresh plus 5. As the speed increases to plus 25, the normal ground segment increases, giving the illusion of being low. As the speed is reduced to V-thresh minus 5, the visual segment is reduced and the impression is one of being high. Speed is returned to V-thresh plus 5. At approach speeds, 5 knots of speed change results in 1 degree of body angle change. Static study of the effect of aircraft heading on visual ground segment. Aligned with the runway center line to 12 degrees right, to 12 degrees left, and return to alignment. 1,200 feet visual range, night. Because of the slope of the glare shield, the visual segment varies with aircraft heading. As the aircraft yaws 12 degrees to the right, the visual segment increases as viewed through the captain's windshield. Yawing to the left decreases the segment. Perspective remains constant because the plane has not moved from centerline. These variations may appear small, but when working in 1200 RVR, they are a significant part of the whole. Now a static study of the effect of lateral displacement on visual ground segment. On center line to 75 feet right, to 75 feet left, and return to center line. 1,200 feet visual range, night. Notice the perspective change as the aircraft moves off center line. This 75 feet displacement illustrated here would be farther off course than should be tolerated at decision height if a landing is to be made safely in 1200 RVR conditions. A diagram of the effect of pilot eye height on visual ground segment for 16 and 45 feet above wheel position. Both of these diagrams are predicated on the same cutoff and body angle. They represent 100 feet decision height with 1,200 feet visual range. The upper diagram has a 16 feet eye height above wheel position as on a 707 or DC-8. The lower one has an eye height of 45 feet above the wheels of an aircraft such as the Boeing 747. The 707 visual ground segment would be 737 feet, while the visual ground segment for the 747 would be only 623 feet. A change in eye height of only 30 feet resulted in over a 15% reduction in the visual ground segment. Later in the film, there are several approaches that further illustrate the effect of altitude on what you will be able to see under low visibility conditions. Normal centerline approaches and landings taken at 16 and 45 feet eye heights above wheel position, 1,200 feet visual range, night. This approach is for an eye height of 16 feet above the wheels. Notice you will see the approach lights slightly before reaching the 1,000-foot bar. 1,000-foot bar, 500-foot bar, threshold, touchdown zone. This next approach has been photographed from an eye height of 45 feet above wheel position. Because the pilot is riding about 30 feet higher than the last approach, he will not see the approach lights until inside of the 1,000-foot bar and closer to the 500-foot bar. 500-foot bar, threshold, touchdown zone. This clearly illustrates the reduction of visual ground segment with increased eye height. Missed approach caused by lateral displacement from which it would be hazardous to attempt landing. 1,200 feet visual range, night. The following approaches are auto-coupled down to decision height of 100 feet. The inbound course is 281 degrees to a sea level airport, altimeter 29992 inches, approach speed 135 knots or V-thresh plus 5. During these approaches, instrument scanning and outside visual checks will be made much as a pilot would make them. However, these checks must be slower and longer than real because you pilots are not initiating the scanning action. Expanded localizer and glide slope are centered. (200 feet above minimums), on center line, on glide slope, no lights. Middle marker. Expanded localizer shows us drifting to the right. There are the lights on our left. Expanded localizer beyond limits, autopilot off, and execute a missed approach. Approach and landing with lateral displacement within limits, 1,200 feet visual range, night. 400 feet, on glide slope and expanded localizer centered. 200 feet above minimums, we'll check for lights. No lights. Middle marker, expanded localizer centered, on glide slope, approaching decision height. Still no lights. There are the lights. We're off to the right. Expanded localizer is within limits. Turn the autopilot off and close gradually on the center line. Touch down and continue a gradual closure. On center line, hold it and roll out. A missed approach caused by excessive track changes. 1,200 feet visual range, night. Approaching 200 feet above minimums. Looking for lights, none. Coming up on the middle marker. Expanded localizer shows us drifting to the left. Expanded localizer at maximum allowable deflection. You look for lights, there they are to our right. Pilot starts an abrupt track change, unable to line up, carries through the center line, and is forced to execute a missed approach. Had he closed more gradually, the approach might have been successful. Approach with aim point adjusted to leading edge of the visual ground segment, resulting in landing short of threshold. 1,600 feet visual range, night. On this approach, the autopilot will be turned off at the first visual cues at about 170 feet. 200 feet above minimums, checking for lights, nothing. Coming up on 100 feet above decision height, again we check for lights. There are the approach lights, autopilot off. The pilot places the visible lights in the normal aiming point of his windshield, thus lowering the nose and going below glide path. Result, a landing 300 feet short of threshold. The eye height is now 10 feet. The landing gear was sheared off in the approach lights. An instrument check, which would have led to the recognition of the previous error. Had either of the pilots noticed that the glide slope was going towards full deflection up as they approached decision height, a missed approach could have been executed and the short landing would have been avoided. A diagram showing the effect of shifting aim point to the leading edge of the visual ground segment. These diagrams represent the captain's windshield on a Boeing 707. The upper diagram is an approach on glide slope where there is a visual aiming point available about 1,000 feet into the runway. Since the aircraft approaches with a nearly constant body angle, the pilot habitually sees this aiming point in the same place on the windshield. In the lower diagram, the visibility is reduced, so the runway aim point is not available. Since the pilot now does not have his normal visual pitch reference, he has a natural tendency to place the leading edge of the visual ground segment, or the visible lights, on his normal windshield reference point, thus lowering the nose and descending below the desired glide path. Remember, without a pitch reference, a pilot is never more than 2/3 visual, so he must use the autopilot or refer to the glide slope until the touchdown zone is in sight. An approach 50 feet below glide slope, resulting in landing short of the threshold, 700 feet visual range, night. As you have seen previously, a lower eye height results in a larger ground segment. Since this approach is made 50 feet below glide slope, we will get visual cues at decision height that would not have been seen had the aircraft been on glide slope. As a result, the pilot will be led into a visual approach that he would never have made had either of the pilots checked their instruments. Approaching decision height. Visual check, nothing. Decision height, another visual check. There are the approach lights. The pilot goes visual but has no horizon or aim point. He is unable to judge the necessary flat glide path and lands short of the threshold. Approach 50 feet below glide slope, resulting in a landing short of threshold. 1,200 feet visual range, night. The aircraft is paralleling glide slope, but 50 feet low. Because of this, you will see the approach lights farther out than normal. You will see them well before the 1,000-foot bar. Also notice the KO lighting allows easy identification of your position relative to the 1,000-foot bar by the presence of red and white lights inside of the 1,000-foot bar. Approaching decision height. A look outside. Approach lights in sight, and still well outside the 1,000-foot bar. With no aiming point, it is difficult to judge height or slope. A landing short of threshold results. Again, had the pilot made sure that he was on glide slope, these early and misleading visual cues would not have been available. Approach 50 feet below glide slope, resulting in landing short of threshold. Runway lighting, U.S. standard. 1,200 feet, visual range, night. On this approach, contrast the U.S. standard with the Akato lighting you just saw. With the U.S. system, the lights are the same on either side of the 1,000-foot bar, except for reds 200 feet from the threshold, making it difficult to recognize which side of the 1,000-foot bar you're on until you see the bar or the red lights. We're paralleling glide slope but 50 feet low. Approaching decision height. Lights in sight. Are we past the 1,000-foot bar as we should be at decision height? No, there it is ahead, and the pilot is dangerously low. He recognizes his position too late. These last several approaches are intended to point out the need for one of the pilots to make continued instrument checks, as well as picking up the expected visual cues to successfully complete a Category 2 approach. Missed approach caused by premature alignment of the aircraft with the runway in crosswind conditions. 1,200 feet visual range, night. The aircraft is on glide slope and centerline, but carrying 12 degrees of drift. This is probably more drift than you would encounter on a Category 2 approach, but it is used here to illustrate a point. 100 feet above decision height, visual check, no lights. Decision height, lights in sight. Autopilot off. Pilot hastily aligns aircraft heading with the runway and drifts off the runway and is forced to execute a missed approach. Approach and landing showing the correct procedure for alignment of the aircraft with the runway in crosswind conditions. 1,200 feet visual range, night. Again, the aircraft is on center line with 12 degrees adrift. This time, the plan is to carry the crab almost to touchdown. By taking it out later, there is little time for the aircraft to drift. "100 feet above decision height, visual check, no lights. Approaching decision height, lights in sight. Autopilot off, but continue the crab angle. Remove the crab and touch down. It is hoped you will review these landing situations you have just seen and study them as they relate to your aircraft and operating procedures.